So you've seen how you can use Pytorch to compute arbitrary partial derivatives for functions that you write. And you could keep doing that. You could always write your own functions out of simple elementary functions, essentially. But when it comes time to train neural networks, we often make use of the same building blocks again and again that are sort of at an intermediate level of description. And so because those things recur, Pytorch makes it simple to build and train neural networks using these standard sort of methods. So let's take a look at some of the options that you have. Earlier today, we talked about the basic features of the optimization problem that underlies learning in deep networks. And we can map those to useful methods and classes in Pytorch. So first of all, when it comes time to implement the input-output function for your artificial neural network, there are a couple options. So you can have a generic neural network module that gives you some basic default settings like weights and biases being trainable parameters. That's quite a generic thing that you can put a lot of different methods into. Or slightly more specific, you can use the neural network sequential container, which basically will take a bunch of modules and connect them one after another in a chain. Very easy to make a deep network using that particular structure. And those are sort of bigger container classes, but then zooming in, what are you going to put in them, sort of the actual modules? Well, you could, for instance, have a linear transformation, so that would apply a linear transformation from some input vector to some output vector, and basically multiplying by a weight matrix. Or you could apply an element-wise nonlinearity like the rectified linear unit. Once you've built the input-output function from those components, and there are many others, then it's time for your loss function. And again, you could write your own, but there are several standard loss functions that are sort of considered best practice for different types of data. And you'll hear a lot more in the course about exactly which loss functions are appropriate for what scenarios. But here are just two. One is the mean squared error. That's just the squared error between your target values and the values the network is producing. That's appropriate for regression tasks. And then another one here, is the cross-entropy loss, which is appropriate for classification tasks. There's a lot more to say about those, but know that there's a whole library of loss functions waiting to go. And third, we can look at the optimization problem. You could always write the loop yourself to do gradient descent, but we have tweaks on that that tend to work better, and you shouldn't really have to write that loop yourself since it's so standard, and so you can use, for instance, these built-in optimizers like the stochastic gradient descent optimizer or the atom optimizer. So if you were trying to build a neural network that looked like this is sort of a very standard deep network. It takes in some input vector x, which is a vector of length n1, and it's going to apply some linear transformation and then a nonlinearity f to get the activity h1 at this hidden layer. And it's going to keep doing that all the way up to some output layer. At each of these layers, we're applying some kind of nonlinear function. Maybe it looks like this, something sigmoidal or 10h. This is sort of your basic, most vanilla deep neural network, the place that I guess it kind of all started. You can build that using these tools, and it's what you're going to do now. You implement your own training loop using these components so that you can see that it's actually quite easy to put these pieces together into standard neural network structures.